Let's focus on order clauses and how they relate to the optimization of queries. We know that to order the information to be queried and returned, the syntax of the for each allows us to specify a list of conditional clauses and an unconditional one. Let's go from what's simpler to what's more complex. We'll start by analyzing the case of a single order clause with no conditions, such as this one. We want to run through the table of tourist attractions, filtering those corresponding to a given country and city, and to display them sorted by attraction name, a secondary attribute. When specifying what we want, it shouldn't matter whether in order to get the required data, it should be first obtained and then sorted, or if it's done the other way around, or in some other way. We, the developers, specify what we want, and the GeneXus specifier, and above all the DBMS, will solve it. When we ask GeneXus to specify and generate the program associated with the object containing the for each, we do it for a given environment. That is, in a given programming language, such as .NET. And for a database managed by a given DBMS, such as SQL Server, for example, it could also be for a Java environment against Oracle, or so many other alternatives. When a developer writes a for each, they do it in GeneXus, with a certain independence from what the final environment will be, in order to obtain the application in different environments with the same code. This means that the specific implementation is handled by GeneXus, which is aware of the specific features of each environment. However, its knowledge has a limit. It knows the database structure, but not the data, nor its distribution, quantity, and so on. This information is held by the DBMS, which records statistics, and caches data and queries in the history of the queries that have been made, builds execution plans, maintains indexes, and so on. The more evolved and intelligent the DBMS is, the less it will need GeneXus to tell it precisely how to perform the query, because GeneXus will never know more than it does. So, for example, if we ask to specify the object that contains this for each, we will see this navigation list, which warns us that there's no index for the attribute by which we want to sort the query, and that therefore we might notice a lower performance. We might doesn't mean that this will indeed be the case. Why? Because it depends not only on the amount of data in the table, but also on the DBMS and its strategies. The navigation list shows the worst case scenario. Here, the whole table must be run through, ordered by an attribute for which there's possibly no index. GeneXus doesn't know if the DBMS created it or not, and has no information about it. So, in the worst case scenario, which is that of centralized architectures, it may have to temporarily create the index to solve the query in that order, and thus run through the entire table to evaluate each record individually to determine whether it meets the filters or not. This would be the scenario of a poor database management system. Let's think, for example, that in this case, using the foreign key index, country ID, city ID, which we know exists because GeneXus forces it to be created, might be a better strategy. Then the records that meet the filters are obtained in an optimal way, and, with that result, it's sorted by attraction name. The best strategy will depend largely on the distribution of the data. If there are only 3 attractions from that country and city out of millions, this seems a better strategy because the cost of sorting 3 records is insignificant. However, if there are millions of records in the table, and most of them are from that country and city, using the index by country and city will not significantly reduce the query of the entire table. Therefore, sorting the result by attraction name will almost be the same as sorting by attraction name and then evaluating each record individually to determine if it also corresponds to the country city or not. GeneXus doesn't know the data distribution to make these kinds of decisions. In addition, if the same query has already been performed before, the DBMS will probably cache the result and will not have to perform the query in the same way again. This is, of course, if the filters and the data do not change. Ultimately then, the navigation list provides information based on the most conservative scenario, with the worst DBMS. However, it's possible that the DBMS will greatly improve the most pessimistic scenario, and the query will be optimized. We might be tempted to think that if we know there will be millions of records in the attraction table, it'll be best to instruct the DBMS from GeneXus to create the user index by attraction name. In that case, the database will be reorganized, and when the object is specified again, GeneXus will inform us that it'll use the new index to solve the query, and the performance warning will no longer be shown. However, this can be a much worse solution. Precisely, if the DBMS is intelligent, it will not need to be forced to create an index at all. It'll do it itself if necessary. So much so that even in this case, in which GeneXus itself requested the creation of the index, it doesn't send it to the DBMS when it performs the query from an environment with an intelligent DBMS. Just look at the source generated for the net environment against SQL Server. In the select statement, no information is being sent about the index to be used. Why would it send it if the DBMS knows it exists? If it needs it, it'll use it. And if it doesn't, it's because it'll use a better strategy. We may suppose that the case would be different if the DBMS was not intelligent. We must take into account that creating an index is costly, not only when creating it, but also later on when maintaining it during the whole life cycle of the table. Every time the table is updated, a small price is paid to maintain it. That's why creating user indexes doesn't seem to be a good practice unless they're needed to control uniqueness, that is, to define candidate keys, such as unique indexes. So as we said, the GeneXus specifier does the best it can with the information it has, and with its current intelligence, it's expected that this intelligence will increase as GeneXus evolves. It sends the query as optimized as possible to the DBMS without providing obvious information, knowing that in the worst case, it'll take it, but in general, it'll improve upon it. In short, we can never be sure that what's shown in the navigation list will be what the DBMS will finally do if it's intelligent. What we do know is that it'll be that or something better. Let's take a look at examples of the current intelligence of the GeneXus specifier regardless of what the DBMS ends up doing later. We know that the order in which the resulting records will be returned is determined based on the developer specification in the order clause, but also on internal optimization algorithms. For example, if we didn't care about how the attraction names will be sorted, we could write the for each without the order clause. In general, we knew that if we did this, the query would be sorted by primary key. That is to say, a select with attraction ID order was sent to the DBMS. However, in this case, something different will happen, as we can see in the navigation list. We know that the database has an index by country ID and city ID, the two equality filters. We know this because they form a foreign key. Clearly then, it'll be preferable to use that index and return the query sorted by those values. That's why, if we look at the query sent by the source to the DBMS, we find this order by. If not specifying the order clause meant that we wanted the queries to be sorted by primary key, in this case, we will have to make it explicit. Similarly, if now the query is this other one, where we're asking for the attractions to be sorted by city identifier, and we're only filtering by country identifier, we will see that the navigation list will not ask to sort by city ID, but by the pair. In this way, it optimizes the query as it knows about the existence of the composite index, because it's a foreign key precisely, without failing to achieve the sorting result requested by the developer. In short, with the order clause, the developer indicates the order in which they want the records to be returned. But for this, the specifier could alter this clause, complementing it with contextual information, if there are implicit or explicit equality conditions, and there's an index that contains them, in addition to the attributes of the order. This is in order to optimize the query, although the DBMS will have the final word. It's important to understand that the data will be returned in the order specified by the developer, even if other criteria are used to solve the query. In this case, where no order was specified, Since there's an index that allows optimizing these conditions, it's chosen instead of the index by primary key. When there is no index, it chooses the primary key. Here we see the SQL statement created by GeneXus. Unless we specify an order none clause, in which case we leave it up to the DBMS to choose the order. Order by is not added to the SQL statement created by GeneXus. Let's go back to this example. If GeneXus asks to create this composite user index, then it'll propose it in the navigation list, even if, in the end, it doesn't send it to the SQL server, because the SQL server already knows about its existence, so why tell it something it already knows? What's remarkable is that it notifies us that at least this optimization will be performed by the DBMS. It'll be like this or better. On the other hand, if the user index does not exist, the navigation list will show us this other one, even if the source is exactly the same. So, let's say it again. The navigation list shows the worst case scenario. If the index exists, we know that the worst case scenario will be pretty good. That's if the index was previously created for some other reason, so we take advantage of it. Creating the index just to make sure this navigation is optimized doesn't seem to be a good idea if we're using an intelligent DBMS. And neither if the DBMS was not intelligent, but the table had few records. In short, create indexes only after noticing performance issues and evaluating the pros and cons. Here's another example of the way GeneXus tries to make improvements. If we want to get all the city names for which there are tourist attractions, we use the unique clause by country ID, city ID, so that of all the attractions that share a country and city, only one is left, in order to list its city name in the output. If we want this output to be sorted by city name, we place the order clause and see that in the navigation list, the specifier writes exactly that order, for which it doesn't know any index. It'll be up to the DBMS to optimize this query. On the other hand, if we don't care about the order in which those cities are displayed in the output, then let's see that by not writing it, the specifier chooses to sort by the attributes that we're asking to be unique, since it has an index by them. Now let's review the conditional order clauses. From this web panel, we want to list the tourist attractions while allowing the user to filter those of a given category, such as tourist site, of a given country, and whose name comes after a given value. So by pressing the button, we call this procedure, passing it the three variables. If the user doesn't enter a value in one of the filter variables, we won't want that filter to be applied. And that's why we condition the three where clauses. If, regardless of the filters applied, we wanted the attractions to be displayed sorted by attraction name, then we would write a single unconditional order clause. Let's run the web panel that we set as main to make it easier to run. In the navigation list, we see that the filters are shown in the constraints section. This is not only because there's no index for optimizing, but also because they contain the when conditions. All where conditionals will be displayed in the constraints section, but that doesn't mean that the query will not be optimized. We'll come back to this. Here's the list of all attractions, since none of the three filters will have been applied. Note that they're listed sorted by attraction name as requested. If we now ask to list the attractions in category 3, which is tourist site, the result is also shown sorted by attraction name and not sorted by country. But let's suppose that if we don't filter by category, that is, this variable is empty, we want them sorted by category name, and that, instead, if a value is selected for category ID, for example, tourist site, we want it to be sorted by country name if no country was selected. That is, this variable was left empty. Also, only in the opposite case, when filtering by category and country, we want it to be sorted by attraction name. Note that the navigation list shows the conditional order clauses, where the last one is unconditional. Unlike the where clauses that do an and between them, only one of the order clauses will be applied. For this, the first condition that's true will make its order clause the chosen one. It'll only be ordered by the unconditional one if none of the conditions of the previous order clauses are satisfied. Of course, we might not place an unconditional order clause, and there the order would not be defined if none of the conditions are met. We can quickly see that if we don't select a category, it'll be sorted by it. On the other hand, if we do select a category and leave the country unselected, then it'll be sorted by country and not sorted by the rest. If we now select category and country, it'll be sorted by attraction name. If we look at the source, to see how the SQL statement sent to the manager is built, we see that first it assembles the first fixed part of the select, that of the attributes to be selected, and from which tables with the joins to access the extended one. But then, it dynamically complements the where part from the evaluation of the variables, adding where when the variables are not empty. And for the order by of the SQL statement, it does something similar, only with nested if to reflect exactly what we said before. Only an order clause will be added to the select. These evaluations to obtain the final SQL statement that's sent to the DBMS to solve the query are done dynamically at runtime. Every time this list is run, this section of code must be executed to build the final query. If this for each were included in another repetitive structure run for millions of records, the cost of dynamically building the query could be significant. In the previous example, we used conditional orders because we wanted to display the information sorted differently based on conditions. That is, the order clauses fulfilled a logical requirement of the query. You could say they were part of the wording of the problem, even though they were not necessary in this case. So, let's think that it was enough to choose this unconditional order to meet the requirement. But many times, as we saw for the case of a single unconditional order clause, it's specified for optimization purposes and is not a requirement. In these cases, choosing filter-compatible orders is usually a good practice, especially in the case of unintelligent DBMSs. For example, if we didn't care about the order in which the information would be listed, we could place these other order clauses. This will translate dynamically as follows. If category ID is not empty, then we know the query will be similar to this one, where, depending on whether country ID is empty or not, and whether attraction name is empty or not, the final query will look like this, or like this. Note that in any case, since there's an index by category ID, at least the first where clause will be optimized. On the other hand, if category ID is empty, then if country ID is not, the query will look like this, or like that, depending on whether attraction name is empty or not. In either case, it'll be optimized in relation to the filter by country ID, since it has an index because it's a foreign key. If country ID is empty as well, then, if attraction name is not, the query will look like this. And if it is, it'll look like this, but the order will be undefined. This means that it can vary depending on the DBMS and even between successive executions. In the first case, as we're not aware of the existence of an index by attraction name, we don't know how optimized the query will be. The navigation list shows that the filters are still displayed in the constraints section, although we know that depending on the values of the variables, some of them should be displayed in the navigation filters. This is because the navigation list doesn't perform the breakdown we did before. We must understand then that the scenario will be better than it may seem at first glance, without taking into account all of the above. What else can be said about conditional orders? They're not supported in control breaks. They do not apply to legacy COBOL and RPG generators. If the conditions have attributes, they're considered as instantiated. That is, they're evaluated before starting the navigation and do not change in the process. This is the end of our exploration of query orders. Of course, what we saw for the for each is valid for groups of data providers and grids with a base table, as well as for queries within data selectors.